Okay, I don't have a stack of exams with me. It's been a long week. Well, whether it is or not, you'll get them back on Monday. So I'll have them back on Monday, and I will not be. I won't post any scores where you can see them until Monday after I hand them back. That brings back the Jill incident where I gave her 100 less points on Canvas than she got on the test, and apparently there was sobbing all night. And so until I hand it back, I don't release it on Canvas. Only did that once. That's all it took. Okay, questions about today's stuff?
When you explain the Endo product, is the group that adds into the middle, like on bridge, is that always on full wedge?
It doesn't have to be, but usually it is.
And if it were on a dash wedge, would the Endo product then be both of the groups being added on the full wedge?
The opposite, yeah.
Endo is opposite of the middle.
Yes. So yeah, that's the Endo product always has the bridge and the two groups that were added trans to each other. Or actually, it's not, it's anti, not trans is the word. Does that make sense to everybody? What else?
When doing the cyclodiene with alkene, we're going to get the two products, but do you want us, like, in answering completely, I know we're going to get the Endo 100% of the time. Is that something that we have to produce both products?
No, if you're making whatever the stereochemistry of the alkene is going to be carried over.
Right.
So you only there's only one major product.
Okay, so that's right.
Yeah, so you're never going to get the exo product. That's never formed.
So you just using the exo, you weren't really saying right them as both.
No, but if that is called exo and endo. The reasoning for the endo being formed over the exo is beyond the scope of this course. It has to do with molecular orbital theory and I think some frontier molecular orbital theory, which is way beyond what we want to go into. But the exo product is actually forbidden. It's not allowed to be produced. But so first things first. So you can only get endo and exo if you have a cyclic diene. Okay, that's the first thing. This is the first requirement to get the endo product. So what would the product of that reaction be? Okay, one answer is no reaction. Anybody have any other products?
So didn't you get a trans product? You have trans in the reaction?
One more time? I didn't hear
We're
you.
gonna get a brand product because they're
So you would like to draw where do you want your sands to go? Do you want the sands to be bold dash, both bold, both dashed? So bold and a dash. Do we want this here? Do we want these guys to be bold? Okay, there's product B. Anybody have another product? No? Let's see what I can add to muddy up the waters. So there's 4 possible products of that reaction. Okay, cards. So what do we think? Probably need to get bigger. I probably need to print out another set of bigger cards. Okay. So A, B, or C, or D? I'll have to bring the cards on Monday. All right, I have 20 Bs. I thought you get more pride, because that's where I was going to start. I thought you would get a lot more support. But then again, you could be the only right person in here. Although there was a D too. But you're not. So here's where the no reaction answer oftentimes comes into play. When people start learning Diels-Alder reactions, the restriction that the diene has to be cis is sometimes misinterpreted. So when I say that the diene has to be cis, and what I really mean is that the diene has to be S-cis, what that means is that for a normal acyclic diene, there are 2 conformations that the diene can exist in. Okay. If it's not cyclic, it can exist in these 2 conformations. And remember, conformations, 3-dimensional structures that you can get by rotating around a single bond. So this is called S-trans, and this is called S-cis, and the difference in them is the rotation around a sigma bond, which is what the S stands for. So the diene has to be cis, not the alkene. Okay? And that's okay. I would have done this regardless of whether it was brought up, because this is a point where sometimes people get confused. Right? So it has to be in the S-cis conformation, because this is a one-step mechanism where the diene and the alkene have to be perfectly arranged so that those two orbitals on the 1 and the 4 of the diene will perfectly match with the 1,2 orbitals in the alkene. So you can't have it S-cis. You've got to have it perfectly S-trans. Sorry, S-cis. You have to have it perfectly S-cis, not S-trans, because it has to plop on top of the double bond. So that distance between 1 and 4 has to be perfect for the movement of the electrons. Okay. The alkene can be either cis or trans. And what's critical here is that the stereochemistry of the alkene is then transferred over into the stereochemistry of the final product. So in this case, what I'm making is, and if I think I did this in the video, and whenever I do this in class, I go 1, 2, 3, 4, 5, 6, because those are the 6 carbons where the action is. I'm going to bond 1 to 5 and 4 to 6. So over here in the product, you've got 1, 2, 3, 4, 5, and 6. So the double bonds can move this way, and then 2 and 2 going to between 2, 1, 2 going to between 2 and 3. So you can draw it like that. So B is the major product of the reaction.
So is that product not considered endo or exo?
Right.
Okay, that's where my confusion was.
Yeah.
Because in the notes you say cyclic diene endo dicyclic. I was thinking that it had to be either endo or exo.
Right. So there's two different cis issues here.
Yes.
The first cis issue is when, whatever, it's Friday. It's been a long year so far. The S-cis refers to the diene. So that question, if I would have started with a non-cyclic one, I could have gotten somebody saying no reaction. So that's the first issue. Then when we get to cyclic dienes where we do have the possibility of endo and exo, which one's endo and exo of C and D? C's exo. We all agree that C is exo. And then endo is D, and there is no name for B. Because endo and exo only refer to the cis alkene and the cyclic diene. And notice the cyclic diene ties the diene into S-cis. So it'll react a lot faster. I mean, we had a number of issues to overcome in lab this week with the 1,3-butadiene reaction. Normally when I do it, I do cyclopentadiene, because cyclopentadiene will react instantly because it's stuck S-cis. It's stuck in the S-cis conformation because of the bridging. What will become the bridge. Okay. So when you asked before about endo and exo, the endo means that these two groups are anti to each other, and exo means that these two groups, the bridge and the two groups, are going to be what's called syn, which is same side. Cis or trans for acyclic systems. So that's your endo, that's your exo. And then the other one just doesn't have a name. And it doesn't matter whether it's bold, dashed, bold, because those turn out to be actually enantiomers of each other. Lisa?
said this is a different concept, so I guess because you started off writing out the first structure saying that on the essay, DNA was the first requirement for an endo product. So
For the first for an endo product, you have to have two things. You've got to have a cyclic diene like this, and then it has to be a cis alkene. That's the only way you'll get an endo product. And there the choice isn't, there the choice is between endo and exo, but exo's forbidden by molecular orbital rules. I believe Woodward-Hoffman rules, both of which won the Nobel Prize. So that kind of makes sense with those? So our problem in lab this week, well, there are many problems. The first is scale. It probably would have been better to scale up the reaction. Is there a double bond here? So what happened with this molecule is that we could basically we were breaking the bonds in order to form the double bond. So what we had was, what did we have? We had basically the sulfur dioxide, a pair of electrons moving there, this pair of electrons moving there to form SO2, and then having the molecule form the cyclo, or the 1,3 cyclo, or 1,3 butadiene. Now the problem with the butadiene is that once it was made, if it was made in the S-cis conformation, it wasn't going to stay there, because these two hydrogens right here are right on top of each other. So the molecule would have reverted to its more stable form, S-trans, and it would never have reacted with the maleic anhydride. So what we had to do was to provide heat, not only to take the sulfolene and convert it to because I usually use cyclopentadiene, that's what I'm used to saying, the butadiene. So we took the sulfolene, made the butadiene. We had to provide enough heat for that molecule to twist back around and form this structure, and then react with the maleic anhydride to form the final product, which had the C double bond O, the anhydride. And then whether these were bold or dashed was irrelevant, because we would get both. We would have both that group being on a bold, two bold wedges or two dashed wedges, because those are the enantiomers. Right? If I have an alkene, my diene can add from the top face to the bottom face, and it's going to add 50-50, which is going to lead to two different enantiomers. But we know that already, because we said last semester that you can't make a chiral molecule unless you use a chiral reagent. And when you're using a diene and an alkene, there's no chiral reagent to select one enantiomer over another. So you automatically get a 50-50. So either product, the critical part is that these two hydrogens are cis. And I haven't taken an NMR of that product, but when I do, at least in my lab, we'll go through the reasoning of why it's cis, and the evidence is in those two hydrogens peaks. And they're the way they're split. So whether they're bold or dashed doesn't matter. That was the final product. But part of the reason we heated is because we needed to force this back into S-cis. If we would have used cyclopentadiene, the reaction would have been over in about 5 minutes. So. What else? Was there Dills Alders? What else was in today's video?
Benzene.
Oh, the introduction of benzene. That's kind of boring. Right, the snakes. The dream of snakes, of Kekule. It doesn't change. It's always the same thing. Let's see that. So let's just make sure we can do a couple of these Dills Alders. So there's two reactions. Can you do those two Dills Alders? And write the product with the correct stereochemistry using bold and dashed wedges. Sure, you can do a mechanism for it too. Even the mechanism with the transition state. That's as far as we can go. Do we have our answer? Now, if I said mechanism's pretty straightforward, right? We would say pair of electrons moves there, pair of electrons moves there, pair of electrons moves there. Or you could go in the other directions. It doesn't matter. And if I said transition state, the transition state would simply be a dotted line to each of the alkene carbons, and then a dotted line inside of the inside of the diene, and then 2 dotted lines to the, oh, I missed. There should be some dotted lines there. So a circle of dotted lines, and then the 2 dotted lines that are forming the carbon-carbon bonds. So I mean, that's a really easy mechanism. So it probably won't be on the next exam, but it could be. Okay, so let's see, my iPad with the stick pickers upstairs, but don't worry. We have 8 rows.
Can you finish this?
Finish what?
I want to see the finished part.
Oh, I'm going to ask you for the finished products.
Oh.
So we got 8 rows. So if it comes up 664 in my random number generator on my phone, so this way I'm not picking on anybody, we'll go to row 6 and then we'll go up until we find the person. 46. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Caitlin. Yeah, you're in row 4, and we went 1, 2, 3, 4, and then we went back 4, and we came back 2, and we stuck on you. So tell me, give me a piece of the first product.
There's a double bond between carbon 2 and carbon 3.
Okay. You gave me a piece. So now 59. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Rhea. Where do you want the groups?
6.
Okay. 6, what kind of group? A dashed CN?
Yeah.
Okay. And then you can finish it off.
Yeah.
Dashed? A dashed CN. Okay. Does it matter whether they're dashed or bold? No, as long as they are the same. So dash bold, the critical part is the 2 CNs are cis. Okay, there's that problem. Okay, now we'll go to the second one, which might be a little more challenging. 44. 1, 2, 3, 4. Oh.
Do the methyl groups still stay on 2 and 3?
Yes, they should. So if we come to you, you can use that as your way out. Yes, it should look like that. Sarah.
For cyclic diene, does it have to be pentane or?
No, it can be a cyclohexadiene.
Okay.
It can be a cyclohexadiene, which is what this one is. Kyle?
Why is there no bridge?
Well, I haven't drawn the bridge yet. Do you want to draw the bridge? What kind of bridge should be there? 2 wedges from where?
1, 4.
Okay, 2 wedges from 1 and 4. And then what goes in between the wedges? And? So 2 CH2s go in between. The bridge is 2 CH2s. But somebody was like, that was brand new.
Why is it not on the first product though?
Because there's no cyclic product. There's no cyclic dying. If there was a bridge here, if the molecule was like this, then there would be a bridge. But it's non-cyclic, and so there's no bridge. There's only a bridge if it's cyclic. Here's the way we do it. We go 1, 2, 3, 4, and we go 5 and 6. No, we go 6 and 5, the way I did it. So when we draw our 6 carbons, we've got that. As we're going through, we say, what's attached to carbon 1? CH2, CH2 bridge. What's attached to carbon 4? CH2, CH2 bridge. So that's where the bridge comes into play. Up here, 1, 2, 3, and 4, there's nothing attached to 1 and 4. So there's nothing to put in those positions. So I have a CH2, CH2 bridge. So can I do this on more than just a cyclopentadiene? Yes. So this is how we would do it with a cyclohexadiene. Okay. Sarah?
So the CH2s come from so what happens to that bond in between those two CH2s?
It's still there. It's still there. It's hard for me to draw it, but it's still there.
Oh, so they're still connected.
Yeah, they're still connected. Sometimes people might draw it, I don't know, sometimes people might draw it like this. Right?
Okay. Yeah.
They might draw it like that. I'm not a big fan of that, but it's okay.
Or instead of that line, can we just put CH2, like just one CH2?
You need 2 CH2s. Because there's 2 CH2s over here. If there was just one would go there, but there's 2. So you have to put 2 CH2s here.
Can you show the transition state for this one? You wouldn't add.
No, and then I would have that. And I'm not trying to be smart there, right? I'm not trying to be, every transition state's based off that 6-membered ring. So you just put in the groups that are attached to the original 2 molecules, and that's going to be the transition state.
And those lines like that's indicating the bridge that's going to be formed.
Yep.
But
So
they don't
that's-
have to, they just dash it, they're not like solid.
No, the dashes are between these two. The dashes are here, 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 and then between this carbon down here and this carbon over here. And that, so there's a 6-membered ring of dash bonds. Okay. Where am I at? We need to finish the molecule off. 28. 1, 2. Oh, this is going to be fun. 1, 2. So then 1, 2, 3, 4, 5, 6, 7, 8. Hey, John.
The COOH on the benches on page.
Okay.
You also need
Okay. Wait, what am I doing? Okay, same thing. Same thing would be over here. So, in showing you the second molecule, my goal was it doesn't have to be a cyclopentadiene, it can be a cyclohexadiene. It could probably be bigger than that, but we're not going to get that far. You might say, so if it's a 5-membered ring, when I draw it like this. So that's with the bridge with the CH2. It looks like that on its side. What would it look like on its side with a 6-membered ring? It would look like that with a double bond. So again, positions, the down positions, these are the exo positions, and then the ones that are axial down would be the endo positions. So again, this is the bridge. The more complicated the structure, the more difficult it is to determine whether it's endo or exo, because it's hard sometimes to find the bridge. These kinds of molecules, it's relatively straightforward, but when you get into a lot of these bicyclic systems, it becomes more difficult. Like I could say, if somebody just gave me this series of 6-membered rings fused together, you could say, is this the bridge? Is this the bridge? Is this the bridge? And the way we would know is this is the double bond, so it's not the bridge. This has the groups attached, so it's not the bridge. That's the bridge. Then you might say, well, what if there were molecules attached to that bridge, or groups attached to that bridge? Well, they wouldn't be the groups that come from the Diels-Alder. So those fused systems, are actually very, get any essential oil, perfume, cologne, and there's going to be probably at least a half a dozen of those fused systems in there, because those are the compounds that make up the essential elements of an oil or a fragrance. Did I give any examples in the note in the video?
Was it mothballs?
Mothballs would be that's naphthalene for the benzene rings. For these ones, for instance, if you have a methyl groups like this, and you have a double bond here, that molecule is called camphor. So if you go out and grab some pine needles, you'll find some camphor. Reduce the carbonyl down to an OH, and you have what's called isoborneol, which has a similar but not exactly the same smell. And then there's borneol, whether the OH is axial or equatorial, whether it's borneol or isoborneol. And so these fused systems are in all sorts of essential oils. And the only reason I know that is because when I run a GC mass spec of an essential oil, and I find a compound, and then I look at the mass spec, and it says it's this compound, and it shows me the structure, it's always some fused system that I can't picture in my head. Because sometimes it's even a 4-membered ring. So these are all formed in nature by plants doing Diels-Alder reactions. And I think the best example of that is that molecule is called isoprene. I didn't do isoprene in the video, did I? So isoprene can react with itself. So you can take 2 isoprenes and you can do a Diels-Alder on it. And when you do the Diels-Alder on it, you're going to get that molecule, which is called limonene. And so limonene is what you can get if you were to steam distill lemons or lime peels. You would get limonene. It's in citrus peels. I mean, if you have any flavor of Coke is going to have it as a flavoring. It's going to be in orange peels, lemon, lime. If you cold press the peels, you'll get a ton of limonene liquid out, meaning you just squeeze them under high pressure. And then you may have heard of turpentine that they use to clean paintbrushes. It's going to have a very similar structure, but not the nice smell. So there used to be, now you can go to the store and buy tons of citrus cleaners. But back when citrus cleaners were like on late night TV, on the infomercials, they would talk about, oh, you can strip paint with these. Well, they're chemically the same as turpentine. They just smell better. But what plants do is plants will take will take these isoprenes and they'll put them together to form these molecules, which are sometimes called terpenes. And so the deal's all the plant can do with no trouble. So and when it does it, which we're not going to talk about, somehow it creates a chiral center there. Because D-limonene and L-limonene smell different. And you might say, but there's no chiral centers in that molecule, but the plant must have a chiral enzyme that it uses to put those two together to generate the chirality of the limonene. So, I mean, everybody in biology, I don't think plants are necessarily the most interesting of, at least students don't like plants, but they're important. Right? I was at some meeting on Saturday with a whole bunch of JCU alumni doctors, and one of them's like, well, I had the toughest class to get into medical school was apparently botany back then. But now he does pollen counts every day during the summertime, and he's like, this is why botany is important, because you need to know pollen counts to be able to understand why people have the reactions they have. So everything is important, just depends on the context. So plants are important because they produce all these things that we end up using as perfumes and fragrances and everything else. I got 4 minutes.
That was a long week. That's a Friday.
It was a long week, and it's, but I still got 4 minutes. You would not be getting your money's worth if I quit early.
I got 2 minutes. Okay, let's see it.
Well, the thing is, I got 4 minutes, but it's going to be more like 8. Because my clock doesn't work the same as yours. It moves wherever it wants to go. So, I have a question.
We didn't have an answer.
Well, you might by Monday.
Okay.
If I want to give you a take-home quiz on this. So, here's a reaction that doesn't necessarily fit our kinetic thermodynamic reactions that we talked about the other day, right? Because we said kinetic and thermodynamic in the context of adding an electrophile to a 1,3 diene systems. This is not a 1,3 diene system, but it does have a kinetic and a thermodynamic process. So my question would be, for this molecule, could you write the mechanism and then tell me what the kinetic and the thermodynamic products look like. So you got about 2 minutes. Tell me where to start. Unless you already know where to start, and then you might want to hold on to that information so that you can be ahead of everybody else. What? I heard somebody say something. Bromine leaves? Do we want bromine to leave? Why? Your guess is wrong. It's going to leave. But why is it going to leave? What did I hear? SN. This is an SN1 reaction. Why is it an SN1 reaction? Because water's weak. It's a secondary halide plus a weak nucleophile. Right? We can go all the way back to that chart last semester. So secondary nucleophile plus weak secondary halide, weak nucleophile, SN1. So my bromine's going to add or leave. I should probably stop. But so there's my carbocation. What kind of carbocation is that? Secondary and allylic. So what should I do next? Draw the resonance structure for it. You can do that on your own time. But that would be the next thing to do after this, would be to write the resonance hybrid. So now what am I going to do with the water? Add it to both. How many steps? 2, right? Because I got to form oxonium ion. Then I got to lose the H plus to get the final product. Now, can everybody kind of see here that I've set this situation up to be, I'd say, similar to what you get when you do the 1, 2, 1, 4 addition, except this isn't 1, 2, 1, 4 addition. And I would say it's similar, except at this point, it's exactly the same. Right? So what's the kinetic and what's the thermodynamic product for that? And you go back and apply the rules. Would be the... Exactly. Right? So I will ask you to do as your practice problems. We could make it a take. We haven't had any quizzes yet. It's just a different column in the grade book. We'll make it a practice problem that I would like you to finish this off. Give me you don't have to do transition states, just do the, finish this off. But then I should probably give you one to try on your own, right? So there's the second one that you can try on your own from scratch and tell me again what's the kinetic, what's the thermodynamic product for that, and write all of the mechanistic steps. You don't have to do transition states, just give me the intermediates, arrows, resonance hybrid, etc. So if you just take a moment here, about 5 minutes ago you looked at that bottom problem and went, what is he talking about? Right? Because it didn't fit our rules, but now it can. So these two are your practice problems for Monday. And I'll have your exams, and I'll release the video for Monday, probably an hour or so. I'll take your homework problems